recording here. Okay. So let's start with something. Let's start with this. So suppose so again, this is coordinates relative to a basis, and particularly an ordered one. And suppose suppose we have a vector v, 5, -12, 3, and we have a basis. Our basis for R3 is the set of vectors v1, where v1 is 1, 2, 3. v2, which is -4, 5, 6, and v3, which is 7, -8, 9. Okay. And I want to find, I'm gonna call this yeah, I'm gonna call this basis, call it B. So B is the set of vectors, and it's an order set of vectors, so v1, v2, v3. And I want to find the coordinate vector a coordinate vector of v relative to the basis B. So this whole phrase here is boiled down to finding v with respect to B. This is my question. This is what we discussed last time. So how do we do this? How do we start? What's the first equation we have to always set up for this? Right, that's right, in Dupree. So we're saying V is a linear combination of the basis vectors. So we got C1 V1 plus C2 V2 plus C3 V3. So what we're looking for is the coordinate the column vector C1, C2, and C3. That's what we're looking for. So we're really looking for what are the values C1, C2, and C3. We're looking for those. So then this becomes, what does this become? This becomes 5, -12, 3 is equal to C1 of V1 is 1, 2, 3 plus C2, V2 is -4, 5, 6 plus C3, V3 is 7, -8, 9. What does this start to become? It starts to look like, well, it's a vector equation, but then I can rewrite this into a matrix equation. These column vectors become the columns of my matrix, coefficient matrix. Then the column vectors C1, C2, C3. And I have this 5, -12, 3. This is my column, my B vector. This is my A matrix. And I'm gonna call this my column vector C. So I have A multiplied by C equals, it equals this B vector, right? That's what I have. I have a matrix equation. And so essentially the problem becomes find the solution to this matrix equation, which would mean C, which is the solution, the column vector I'm looking for, it would be the inverse of A multiplied by B. And so when I do so, I'm going to use my calculator for this. If it's opened up. So I'm going to go to my matrix and I'm going to edit a 3x3 matrix. And it becomes 1, -4, 7, my first row. My second row is 2, 5, -8, and then 3, 6, 9. And then in my second column vector, in my B, I'm gonna make this a 3x1 column vector, and it will be 5, -12, 3. And then I'm gonna use the matrix of A, but I'm gonna take the inverse of it, and I'm gonna multiply that by the matrix B. And I get -2. Where do we get the B vector from? Yeah, so let me just say, the B vector is just the, go back.
I think I missed that part of the question, that's all.
Yeah, I'm just saying, okay, the reason why I write it this way is just to kind of give you a like a flashback to what we normally were doing in the beginning of the semester, which was to solve a matrix equation, AX equals B. That's all this is, why it's called B. Well, I call this B just to like give you guys a recollection of what we were doing in the beginning. But in reality, this should be V, right? This is A times, and so there's so many ways to like rename the vectors. But
Yeah, but where did we see V being that? Did we define V to as being that? Because maybe I missed it, but did we
yeah,
define V as
V
5,
is
-12,
V.
3?
Yeah, V is 5,
Sorry.
-12, 3. That's the way we started, by saying V was 5, -12, 3, and then we're given a basis, and we want to find
I
what is
missed
the,
that. Thank you.
yeah, no problem. What is the coordinate vector relative? What is the coordinate vector relative to this new basis? So then that's what we're doing. And so when we put in our calculator and we solve the matrix equation, right? So again, this should be V, and you guys can change that if that's, I don't want to confuse anybody. I just did that just to get for you guys to remember what we normally would call it, right? We would normally call that, but that's no problem. This could be returned back to V. The idea is the same. So then the answer was what? We got -201, right? That was our solution based upon our computation done in the calculator, which would mean that C1 is -2, C2 is 0, and C3 is 1. And that's exactly our vector, coordinate vector relative of V relative to the new basis. It's -2, 0, 1. That's what this new vector is represented by, utilizing this new basis. So if my basis vectors are these vectors, then this vector with respect to these basis vectors has the representation -2, 0, 1. So does everybody understand this step, this process? How this goal of ours becomes solving a matrix equation that we've already solved for many times in the beginning of the semester. And everyone clear with that? No questions? Okay. So I hope it's clear. So that's when we deal with vectors and vectors, right? But we can also apply this. We can also apply this idea to polynomials. So what if I have a polynomial 4 minus, yeah, let's write it this way. 2 minus x plus x squared. And this is in P2, right? This is in the polynomial space of polynomials with degree less than or equal to 2. And let's say I have a basis. My basis for P2 is defined to be this. So P1 is 1 plus x. P2 is 1 plus x squared. And P3 is x plus x squared. And what I want to find is the coordinate. I want to find the coordinate vector of P of x relative to the basis B. So I want to find what is P if I were to, so I can write this with parentheses or with square brackets, this thing here, parentheses or square brackets, it doesn't really affect it. I'm just saying I want to find what P is with relative to my basis B. That's what I'm trying to find. Now, how does one do this with polynomials? Is there any difference treating polynomials compared to just treating vectors in R3 space? Yeah, there really is no difference from the setup. The setup is what? P is equal to C1P1 plus C2P2 plus C3P3. The only difference is these P's are polynomials, right? So then I have to treat them as such. So P is 1 is what? 1 plus x. C2, P2 is what? 1 plus x squared. And C3 is what? X plus x squared. And then P was what? 2 minus x plus x squared. But then how do we go on from here? What do we have to do now? Slightly different now in the procedure, but the setup is identical to vectors. So we have to now deal with the structure of this polynomial space because we're dealing with polynomials. And how do we take care of this from here? Set up the matrix, right? So then how do we set up that matrix? Where does that matrix come from? The equations. So then, okay. So then what are the equations that we have? Do we have any equations at the moment? We only have this one single equation. 1 plus x equals 1, 0, 0. Oh, yeah. So the way to continue to get that matrix that you suggest is to distribute the C1. This becomes C1x plus C2 plus C2x squared plus C3x plus C3x squared. This is 2 minus x plus x squared. We're going to combine like terms. So what are the like terms here? We have C1 plus C2. And then we have plus C1 plus C3 x plus C2 plus C3 x squared. Do you see what I'm doing? I'm treating these as polynomials. So I have to be careful with the polynomials. This is the constant. I'm saying this polynomial on the right side of the equation equals a polynomial on the left side. So the coefficients have to line up. They have to match. The constants have to match. So from here, from this step, I get three equations. I get that C1 plus C2, this has to equal 2. I get a C1 plus C3, this has to equal -1. And I get that C2 plus C3 equals 1. Do you guys see what I'm saying? This matches with this. This one has to match with this. And then this one here has to match with this. They have to match each other in with respect to terms, whether it's the constant, whether it's the x term or the x squared term. Now from here, what can I do? I have a system of equations. I can set up the coefficient matrix now. This becomes 1, 1, 0. This is 1, 0, 1. And this is 0, 1, 1. Multiplied by C1, C2, C3. This equals 2, -1, 1. Okay. So this is my matrix. You can treat this as A. You can treat this as X. And you can treat this as your B value. Okay. See, again, this is just from what we've been doing all this other time in the beginning, solving matrix equations. So solving for X, which is the solution, C1, C2, C3, is the same thing as saying taking the inverse of your matrix A and multiplying it by B. And again, you can do this using your calculator. And so you go back, you edit, and so it will be 1, 1, 0, 1, 0, 1, 0, 1, 1. And then you edit the next column vector, which is 3 by 1, 2, -1, and 1. So you go back. I'm going to just copy this command, which I already found. And so this will be 0. Oh, very similar numbers. So you have 0, 2, 0, 2, -1. So this is the coordinate vector relative, a coordinate vector of P relative to my new basis B. So we have 0, 2, 1. 0, 2, 1. This would be the column vector. So it's like saying I need 0 of these, I need 2 of these, and I need 1 of these guys to get me this polynomial. And again, the coefficients, the scalars with respect associated with each of those basis polynomials are the coordinates for my vector that's relative to this new basis. So any questions about finding the coordinate vector of polynomials relative to basis of polynomials? So you see how the step here is similar. It's similar, identical in the setup, but the procedure here is a little bit slightly tweaked because of the fact that these are polynomials. But then eventually I get a matrix equation, and solving this matrix equation now becomes pretty commonplace and straightforward. Okay, any questions about this? Okay, no questions. All right, so then now let's talk about matrices. So suppose, yeah, suppose I have a matrix A, okay? So A is a 2 by 2 matrix, 6, 5, 2, 3. And suppose I have a basis for M22, which is the space of all 2 by 2 matrices. And I have A1. I have A1 is 1, 0, 1, 0. A2 is 1, 1, 0, 0. And A3 is 1, 0, 0, 1. And of course you need 4 because you're in a space with dimension of 4, and I have 0, 0, 1, 0. So these are my basis elements or matrices for the basis of this matrix space, 2 by 2 matrices. So I want to find, what do I want to find? I want to find the coordinate vector of A relative to basis. Let me call this basis B. Okay, which would just indicate that I'm finding what A is with respect to B. That's what I want to find, the coordinate vector. So again, the setup is the same, right? The setup is the same. I want to find A, but this I want to find in the span. I want to know what is the coefficients that cause this to be in the span of the basis matrices elements. So this is A2, C3, A3, plus C4, A4, right? Same setup as the polynomial example and same setup as the normal vector example. But now the difference is what? These aren't polynomials, these are matrices. So what is A again? A is 6, 6, 2, 5, 3. 6, 2, 5, 3 equals C1, and A1 is 1, 0, 1, 0 plus C2 is 1, 1, 0, 0 plus C3 is 1, 0, 0, 1 plus C4 is 0, 0, 1, 0. Now from here, what do we do? What do we do from here? Build the system of equations by, by component or by entry, right? So in the first entry, I can just put this all together into a single 2 by 2 matrix, right? The sum of these 4 2 by 2 matrices with the scalars just becomes what? The first entry becomes C1 plus C2 plus C3. The second entry here becomes C2. The third entry here becomes C1 plus C4, and then the last entry becomes C3. That's pretty nice. So this becomes 6, 5, 3, 2. So then I have 4 equations now. I have that C1 plus C2 plus C3. This equals 6. I have that C2 is equal to 2. I got C1 plus C4 is equal to 5. And I got that C3 is equal to 3. And then I can create a matrix equation from here. I can say this is 1, 1, 1, 0. This is 0, 1, 0, 0. This is 1, 0, 0, 1. This is 0, 0, 1, 0. This here is being multiplied by C1, C2, C3, C4. And then this becomes 6, 2, 5, 3. Right? So see how we went from having a matrix equation, a linear combination of matrices, to now having just one single matrix equation. Okay. Now I want to solve for it. I want to solve for C1. I want to know what C1 is, C2, C3, C4. Okay, and so from here we can, you can do this by hand. It shouldn't be too bad, right? Because C1, C2 is already defined for us. C2 is already 2 and C3 is already 3. So then C2, C3. So if C2 plus C3 here, this is 5. So then C1 has to be 1. And then if C1 is 1, then C4 has to be 4. Oh, that's pretty nice. So then the coordinate vector relative, the coordinate vector of the matrix that we started with A is its relative coordinate vector relative to the new basis B is simply 1, 2, 3, 4. Is that clear? Any questions about this? Clear as day, right? Okay. I just have one question that I would like to see. It has to do with bases. So suppose I have these bases here, P1. There's another example here. It's a bit unrelated to the coordinate relative stuff, but I still want to make sure everyone's clear about this. So P1 is 1 minus 3x plus 2x squared. P2 of x, it's 1 plus x plus 4x squared. And P3x, 1 minus 7x. And then the question actually is, show that the following does not, the following set of polynomials is not a vector, is not a basis for P2. Now remember, we talked about a lot, particularly for the homework, a lot about basis, whether something's a basis, eliminate this vector to create a basis, extend this set to create a basis. So I have 3 polynomials and they're all in the space, they're all belong to the space of P2. They're all polynomials that have a degree less than or equal to 2. So we already know that the dimension, we know that the dimension of P2 is 3, right? We talked about this because it has 3 degrees of freedom. That's another way to determine dimension. And dimension is also equal to the number of basis vectors or elements in the set. So I'm expected to have 3. So that's why I have these 3 candidates. But the question is already saying that it's not going to be a good candidate. It's not, this is not a good set to be a basis. So the question is, how do we show that this is not a basis? What would we have to show? Prove linear dependence. Yeah, that's a good way. And so then how do we prove that? Presence of a free variable, right? That's another thing, right? So see all these things, statements that we've seen before start to now come together, right? You talk about linear dependence, which results in finding the presence of a free variable. But then finding the presence of a free variable, you need to know the row reduced echelon form. So then, but then it's row reduced echelon form of what matrix? So what's the matrix that we have to set up? Well, this starts with setting up the dependence relation, or the linear in the dependence relation, which is C1 P1 plus C2 P2 plus C3 P3. This has to equal 0. In other words, 0 plus 0x plus 0x squared. That's what this 0 is. This is what 0 vector is in the world of P2, right? That's what 0 is. And so then C1 is what? P1 is 1 minus 3x squared plus 2x squared plus C2 is 1 plus x plus 4x squared plus C3 is 1 minus 7x equals 0. Then you do C1 minus 3C1 x squared plus 2C1 x squared plus C2 plus C2x plus 4C2x squared plus C3 minus 7C3x. This all equals 0, right? Then what do? We combine like terms. You have C1 plus C2 plus C3, that's my constant term, plus negative 3C1. No, pardon me. This should be C2 minus 7C3x. That's my constant. That's my linear term, x term. And then lastly, I got negative 3C1 plus 2C1 plus 4C2 x squared. That equals 0. And then from here, I have 3 equations. I got C1 plus C2 plus C3. This must equal 0. I have C2 minus 7C3. This must equal 0. I got minus 3C1 plus 2C. Sorry, this should be 2. Did I write something wrong? I think I did, right?
Yeah, Professor, I was just going to mention up there where you still have them in parentheses,
Yeah.
C1, 1 minus 3x squared plus 2x squared. It's just, yeah, there you go.
Yeah, I made that mistake. So then what's going to happen is you only have 2, right? So this will, you only have, so this one is incorrect. This should be 2C1 plus 4C2. And then here we have a bit more. We have minus 3C1 plus C2 minus 7C3x, right? So then this equation here becomes minus 3C1 plus C2 minus 7C3. I just want to make sure that's okay. And it is. And then lastly, the last equation is 2C1 plus 4C2. That equals 0. Okay. So that's clarified a bit. I don't know why I had 2x squareds term written this way, but now we have it, right? Now we have a system of equations, 3 equations, 3 unknowns. So we got 1, 1, 1, negative 3, 1, negative 7, 2, 4, 0, C1, C2, C3, 0, 0, 0. Now, what we're saying is, what we're saying is that this is not a basis. So if it's not a basis, then what does that mean? That means that this matrix here, if I don't have these C1, C2, C3 being unique, being zeros, then there must be infinitely many solutions, or it's just a no solution. But the thing is, every homogeneous system, the solution is 0, 0, 0. So the idea is that there will be more than just 0, 0, 0 being the solution to this, which would indicate that this has a determinant equal to 0. So there's so many ways to prove the same point. That's what I'm trying to get at. So you can do this in many ways. What I'm going to do is I'm just going to show you two different ways. So second matrix, I just have to edit the matrix again. So my new matrix 3 by 3 is 1, 1, 1. So 1, 1, 1. And then negative 3, 1, negative 7, 2, 4, 0. And then you can find, so I'm going to find the row reduced echelon form of this matrix. Sorry. I'd have to find the row reduced echelon matrix of a matrix. So I have to plug in a matrix. So I didn't do that. That's why I got the error. And I got that the row reduced echelon form of this matrix A. So if I say RREF of A, I get 1, 0, 2, I get 0, 1, negative 1, and I get 0, 0, 0. So what does that tell me? There's one free variable, which indicates there's one free variable indicates that there are infinitely many solutions. If there are infinitely many solutions to the homogeneous system like this, then this indicates that what? That these original polynomials are not linearly independent. They're linearly dependent. So this indicates linearly dependence. And I could have also gone to the same conclusion if I found instead the determinant. So if I take the determinant of this matrix A and I get 0, it gives me the same conclusion. If it's 0, it means that it's non-invertible. And then once it's non-invertible, then there is no unique solution to the system, homogeneous system. So therefore, it's linearly dependent. So we just showed that these polynomials originally were linearly dependent from the beginning. So it can never constitute itself as a basis for P2 because we need 3 linearly independent vectors to be considered a basis. Okay. Okay. Everyone okay with this so far? Everyone good with basis? Knowing how to show something as a basis, showing something something that's not a basis, how to express different vectors with respect relative to other vectors. Yes, Sam.
Yeah, but did you mention there was going to be another way to solve this? Or were you just like trying to say that there's different ways to say the same thing?
Yeah, I'm saying that there's different ways. So yeah, so this A vector here, right? This A matrix, I could have said, oh, the row reduced echelon form produced 2 pivots indicating there's one free variable, indicating there's infinitely many solutions, which would implicate that they're linearly independent, right? Linearly dependent. But then the same thing could have been concluded if you took that matrix and found the determinant, which in this case was 0. So it's kind of like redundant in a way, but I'm just saying that there's different ways to get to the same conclusion. These are all these equivalent statements that we discussed earlier in the semester, right? And all these equivalent statements should be all processed here in your head. So row reduced echelon form, determinants, existence of solutions for systems, all of those things now started to become more and more connected and intertwined. So that's all I'm trying to say. So I could have just found the fact that the determinant of A was 0, which would indicate that there is no unique solution to the system, which would indicate infinitely many solutions, which would indicate or implicate linear and dependent. Okay,
All right, thanks, Professor.
no problem. Okay, so now that we've become more comfortable with basis, what a basis is, it's a set of. Sorry, so there's somebody out there with their mics on. Let me just mute them. So again, so we've talked about what a basis is. It's a set of linearly independent vectors that span the space, right? So if you're a spanning set while at the same time being linearly independent, you automatically become a basis. The number of those elements in that basis set of vectors that constitute the basis, those number of elements indicates the dimension of your vector space that you're dealing with. And the dimension also is a way to express the degrees of freedom in that vector space. And pardon me. And we see that there's different bases for a given vector space. There is no one unique basis. You can create an infinite number of bases that are can express vectors in particular vector spaces. So because of that, there has to be a way where we can go from any sets of bases to another set of bases. So if we have one set of bases and we have a vector relative to one set of bases, and then I want to find the same vector now in a new relative to a new basis, I want to be able to go from either or. So that's the new step. That's the new level. So we're going to be dealing with change of basis matrices. So now the matrices that we're dealing with are going to be matrices that help us transition from one basis to another. So this gets interesting pretty quickly. So what's the idea? Okay, so this is called the change of basis. So I'm going to have what's called the old basis. It's not old because of anything to do with age, but it's just because we started with it. So I'm going to call this B, right? And this is just like the general idea of this, okay? Just to give you an idea of what's going on. So let's suppose, it's going to be an arbitrary example. Let's suppose my basis I have is U1, U2. Okay, so I'm in a vector space. So U1, U2 is in a vector space V where the dimension of V is 2. Okay, so we need two vectors that are linearly independent that span the vector space, and we have them. So the basis here is U1, U2. Okay, and then we have a new basis. So we start with one basis, and then we want to go to a new set of bases. So I'm gonna call this new set of bases B. I'm gonna call it B prime. Okay, and then the vectors here are going to be V1, V2. So to avoid confusion, actually, I'm going to write this as, what should I write this as instead? There's never a good way to do this, huh? So I'm just going to write these as W's, okay? Because U and V, they look very similar. So W1, W2, okay? So W1, W2 are also vectors in my vector space. Yeah, W, right? Yeah, W is good. Okay, so I have this new basis set of elements, vectors, W1, W2, and I have this old one, okay? So the idea is what you're gonna do is represent. So we're gonna represent the old basis vectors relative to the new. So we're going to represent the old ones relative to the new basis. Okay. So what that means is I'm going to take U1. I'm going to write it as a linear combination of the new basis. So what is that new basis? Again, this is an arbitrary thing. So I'm going to call this A, W1, and then plus B, W2. Okay. And then U2, I'm going to write this as C, W1 plus D, W2 for some scalar A, B, C, and D. Does everybody follow me? Which would indicate that U1 with respect to the new basis is AB, right? Now we're going to be dealing with this idea of relative coordinate vectors relative to bases much more seamlessly throughout this. This is U2. U2 with respect to the new basis is what? CD, right? So far, this is just from the definition of coordinate vector being relative to a new basis. Okay, so my old basis vectors are being represented in terms of my new basis vectors. Does that make sense? So far, so good. Okay, so now let V be some vector in V, right? And suppose I represent V now in terms of the old basis. So represent or express V as a linear combination, linear combination of the old basis. So then this will be V, right? V will be equal to, I'm going to use these letters now. C1, U1 plus C2, U2, which would mean that V, in terms of their new, in terms of the old basis, is C1, C2. There's a lot of letters in this, okay? But you can stop me at any time to make sure you understand what the letters mean. So we have an old basis called B, U1, U2. We have a new basis called B prime, W1, W2. We represented the old basis vectors in terms of the new for some scalars A, B, C, D. And then we express some arbitrary vector V in terms of the old basis. And we're gonna get somewhere with all of this. So then the question is, why do we care about finding these relative coordinate vectors? Well, the reason why is because now, what was U1 and what was U2? I can represent now this. So this arbitrary vector V is expressed in terms of the old basis. And now I can also represent the new basis. I can represent V in terms of the new basis. So now how about V? So now find V relative to the new basis. How would I do that? Well, since I know V is equal to C1U1 plus C2U2, then I can replace U1 in terms of the new basis vectors, which is what? A W1 plus B W2 plus C2, and U2 is what? C. Okay, I see. So I'm not going to use C in this case. I'm going to use some other number here called K. K. Because then I don't want to confuse anybody with the C's here. So C, right? So K2 is C W1 plus D W2. And then when you rearrange certain things, this becomes K1A W1 plus K1B W2 plus K2C W1 plus K2D W2. And if you combine like terms, W1 with W1 and W2 with W2, you get K1 A plus K2C W1 plus K1B plus K2D W2. Right? And so then what is V with respect to the new basis? This becomes what? K1A plus K2C. And this becomes what? K1B plus K2D. Everybody with me so far? Does anybody understand what's going on at this moment? There's a lot of letters here, but don't get bogged down by the letters. Try to understand what the letters represent. Now, so all of this is related to the idea of coordinate vectors being related to bases, right? So this arbitrary vector that we found in V has a coordinate relative to the old basis. The same vector that we have that we arbitrarily chose in V that has this expression in terms of the old basis has this expression in terms of the new. So this is old relative coordinate vector, and this is the new coordinate vector relative to the new basis, right? And if you look at this here, I can rewrite this as a matrix A, C, B, D being multiplied by K1, K2. Does everybody see that? Yes? We went from this to this matrix. Do you see how they're equivalent? They're the same? Okay. Now, let's do a few more things. So this V, B prime, is equal to ACBD. But wait a minute, what is K1, K2? K1, K2 was what? The relative coordinate vector with respect to the old basis. So look what we discovered. We discovered that if we have the coordinate vector relative to the old basis, let's write this out. So this is the coordinate vector relative to the quote unquote old basis. And then we can multiply that by some matrix, which results in the coordinate vector. This is the coordinate vector relative to the coordinate vector of V, the coordinate vector of V relative to the old, this is a coordinate vector of V relative to the new basis. And this matrix in here is called a transition matrix. So that's the new thing. It's the transition matrix. And we call this transition matrix, we usually call it P. Okay, this is the matrix that takes it from, sorry, this is a transition matrix from B to B prime. And this is denoted by P. Does everybody see that? So we have a transition matrix. And to be even more specific, what was AB and what was CD? AB was what? The coordinate vector relative, the coordinate vector of the old, one of the old vectors in terms of the new. CD was the coordinate vector of one of the old, of the other old basis vector in terms of the new. So if you want to create a transition matrix from the old basis to a new basis, the way you do that is by getting columns of vectors where each column of the vector is the representation or the coordinate vector relative to the new basis. So let me just rewrite that. So this is V, B prime is equal to the old basis in terms of the new, the old basis in terms of the new. Multiply that by V, old basis. This looks kind of crazy, doesn't it? Yeah, it is kind of crazy. So I think we should definitely make this a bit more concrete. So we're not going crazy. Okay, so let's have a very concrete example. So I'm gonna have an old basis, okay? And again, the old basis is just a basis that we start with. It could be anything. So an old basis, suppose we call this B, and our U1 and our U2 bases vectors are the following. U1 is 2, 2, and U2 is 4, -1. Okay, so these are specific vectors that are constitute a basis in R2. And then let's have our new basis be B prime, and let's call those W1, W2, and W1 is 1, 3, and W2 is -1, -1. Okay? So first of all, there's several things we have to do. The first thing I want to do is I want to let some vector called V. I'm gonna call some vector V. This vector is gonna be 3, -5. Okay, 3, -5. I want to find the coordinate vector of V relative to B. Okay, so this is the old. So how do I find that? Let's take this step by step. How do we find that? How do we find the coordinate vector of V relative to B? What do we have to do? This should be the easier part of all of this because we've done this already. So what do we have to set up? What's the equation? Remember, I'm finding this, right? V in terms of B. That's what I'm trying to find. So what is that? How do we start this? V, yep. So we can say V is equal to, I'm just going to use C1 in this case. C1 U1 plus C2 U2. Which is the same thing as saying 3 negative 5 equals C1. U1 is 2, 2. And then C2 is 4, negative 1. This becomes 2, 2, 4, negative 1. C1, C2 equals 3, negative 5. And so then what does C1, C2 become? You know what? Yeah, let's leave it as A, B, because we're gonna have to do this again for the other bases. So this is A, B, this is A, B, and this is A, B. So when you do that, what do you get? So again, I would recommend just doing this using your calculator because it's quicker. So I do 2, 4, 2, negative 1. And then a 2 by 1 matrix, which is 3, negative 5. And so I get this, if you guys verify with me, A is negative 1.7 and B is 1.6. Negative 5, right? Did everybody get this? So this indicates that V with respect to B is what? Negative 1.7, 1.6. Right? That's the first thing I want to establish. The second thing I want to establish is how do we get these numbers? Well, we solve this equation, matrix equation. So I'm gonna, like, in certain regards, I'm gonna skip over the details because we've seen these, we've been solving these equations so much, right? So it's kind of almost like second nature now. When we have a system of equations like this, I want to solve for AB. So then I put this in my calculator, I take A inverse, right? This becomes A, I multiply this by A inverse, and I get this as my result. So you can check using your calculator that these were are indeed the coefficients A and B that create this linear combination for this vector V. So then these numbers here are the coordinates, vector coordinates, or the coordinates of the vector relative to this new basis. So this new basis that I have, this old basis, pardon me, the old basis that I have, this vector V in terms of these basis vectors has this coordinate, coordinate relative to it. These are the coordinates relative to that old basis. Now I'm going to find the same thing, but now for find the coordinate vector of V relative to the new basis. So what's the coordinate vector of V relative to the new basis? Well, I have to figure that out the same way I figured out the coordinate vector to the old basis. So now I'm going to use, instead of A, I'm going to use C times W1 plus D times W2. This becomes 3 negative 5 equals C1. Now W1 is what? 1, 3 plus D, and W2 is negative 1, 1. This matrix equation now is 1, 3, negative 1, negative 1 times CD equals 3, negative 5, which now the problem is similar to the one we just had above. I'm going to create a matrix using my calculator. 1, negative 1, 3, negative 1. And then the column vector here would be, again, 3, negative 5. And then when I perform this, I get negative 4, 7. So I get V with respect or relative to the new basis. The coordinate vector is negative 4, negative 7. Okay, so we can do this individually, no problem. These are small numbers. This is a small vector space, two-dimensional vector space. But then the issue becomes when you get bigger vector spaces, you want to find a way to directly transition every vector from one relative to one basis. I want to be able to do that transition to another basis just by seamlessly multiplying by one single matrix. And that's the idea. So then I want to find the transition matrix. Okay, I want to find the transition matrix from the old to the new. Now, how do I do that? Well, remember what we talked about in the more general example. These column vectors are what? These column vectors are the coordinates relative. They are relative to the new one. So I have to do a bit more work here. I want to find the old. What is the old? The U1, U2. I want to find the coordinate vectors relative to the new one. So if I call this, what do I call this? We don't have enough letters in the alphabet to do this right. T's no good, W's no good. How about U? No, X, no. Do you guys have a good letter for this? So I want to write this in terms of W1 plus W2 W1 plus W2. R? Yeah, I was thinking about R. R. Yeah, so let's do that. Let's do RS and then call this like MN. Doesn't really matter, but so now I want to find what this stuff is. I want to find U1. What is U1? 2, 2, right? So 2, 2 equals R times W1. W1 is what? 1, 3 plus S times -1, -1. So I want to write this. 1, 1, -1, 3, -1. RS equals 2, 2. So then what's going to be R and what's going to be S? So again, it's the same system of equations, the same kind of problem again and again. So in this case, I got 1, -1, 3. Yeah. Let me just see one. Yeah. And then the new column vector is 2, 1, 2, 2. So when I got that, I got 0, -2. What does that mean? That means that U1 with respect to the new basis is the same as 0, -2. And then I'm going to do the same exact thing here. This is m times 1, 3 plus n times -1, -1. The resulting equation would be 1, -1, 3, -1. Mn, in this case, U2 is what? U2 is 4, -1. And I want to find what is M and what is N. So when I do that, 4, -1, my calculator, and I get -2.5, -6.5. So the coordinate vector relative to the new basis is -2.5, -6.5. Now, why do I care about this? Because these are going to be what? These are going to be the columns of my transition matrix. So the way we denote that is by saying P. We're taking B and putting it into B prime. So this is old to new, right? This transition matrix is from old to new. From old basis to new basis. So what is my transition matrix going to look like? It's going to look like the columns is going to be the coordinate vector of U1 with respect to the new basis. Then the next one will be the second old basis vector with respect to the new one. And we found that to be 0, -2, -2.5, -6.5. So that's the third thing, right? So then to put it all together in conclusion, what would be the conclusion of this? We have that. We have what? We have the coordinate vector with respect to the new basis of the given vector v is equal to the transition matrix B to B prime. This transition matrix multiplied by the coordinate vector relative to the old. And I want to just verify that. So we verify How do we verify this? Well, what was the coordinate vector with respect to the new basis? It's -4, 7. So this is -4, comma, -7. So is this equal to the transition matrix, which is 0, -2, -2.5, and -6.5? Is this the same as being multiplied by the coordinates of the old matrix, the coordinate vector relative to the old basis, so -1.7, 1.6? It's -1.7, 1.6. Yeah, positive, pardon me, positive. So is this true? Well, you can compute this in your own, either by hand or using your calculator, and I'll use my calculator for this. You got 0, -2.5, -2, -6.5. Does everybody have any questions about this? Do you guys follow what I'm doing? It's a bit more involved. It's not just doing it one time. You're doing this several times. If you put this in your calculator, yeah, we're not in calculus anymore, right? We're not in Kansas anymore. So if you do the actual computation, 0 times -0.7 plus -2.5 times 1.6, and then -2 multiplied by -1.7 plus -6.5 times 1.6. If you do the computations, you do indeed get -4, -7. So this just verified the fact. This verified the fact that this transition matrix that we found is indeed the transition matrix that takes the coordinate vector relative to the old basis, and when you multiply this, gives you the coordinate vector relative to the new basis. So why is this good? Because now I can, in a sense, I can disregard step 2. I don't have to do step 2 any further ever again, as long as I have the transition matrix from the old basis to new basis. I can always apply that matrix to any vector relative to the old basis, and I get the coordinates relative to the new basis. So the most computationally intensive part of this problem is finding the transition matrix. That becomes the most difficult part. As you can tell, to find transition matrix here, I had to do the coordinate vector relative procedure twice. And if I have if I have 3 basis vectors, then I would have to do it 3 times. If I have 10 basis vectors, I have to do it 10 times. So that becomes that becomes computationally intensive. And I have to do a lot of these matrix equation solutions, find the solutions to the matrix equations more and more, right? As the number of basis elements gets bigger and bigger. So there has to be a better way. There has to be a better way of computing the transition matrix. So what is that way? It's very interesting. So more, I would say, efficient procedure for computing the transition matrix. P as B goes to B prime. So the way to do this will give you kind of some, make you remember of it, or it's reminiscent to the way we find the inverse of a matrix when we first learned how to find the inverse of a matrix by augmenting the matrix that you finding the inverse of with the identity matrix, right? And so we had a matrix A, and then on the other side of the little line that we had the identity matrix, and we performed row reduced echelon form. So then the left side A became the identity, and the right side became a inverse, right? So that step is exactly what we're going to do here, except that now we're going to have a different kind of setup. So create a matrix where the left side is the old basis vectors, and the other side would be the new basis vectors. And so actually, let me see. It's the other way around. It's the old with the new. So it's the new on the left side and the old on the right side. So once we create that matrix, then we perform Gauss-Jordan elimination. In other words, we perform row operations to the point that this matrix now becomes the identity. And the thing on the right is exactly the transition matrix. From B to B prime. So we get the identity with P, B to B prime. And just to make sure that this is indeed okay, let's do that with this example. So going back to the example, the idea is that we have the new basis vectors. What are my new basis vectors? They were 1, 3, negative 1, 1, negative 1, right? So these are the new. These are the new basis vectors B prime. And then on the right side are the old ones, 2, 2, 4, negative 1. And so these are the old basis vectors B. Okay. And so then I want to find the row reduced echelon form. So I want to perform row operations on it to get that. And I'm going to use my calculator for that just to show you. So I'm going to go second matrix. This is going to be a 2 by 4. Not a 2 anymore. A 2 by 4. And I got 1, negative 1, 2. Wait, whoops. No. So this is 1, negative 1. What? Oh, sorry. This would be negative 1. Yeah. And then we got 2. We got 4. We got 3. We got negative 1. We got 2. And we got negative 1. Okay. And so then when I perform the row reduced echelon form function from the calculator of my matrix A, I get 1, 1. I get the identity, which is exactly what I expected. And on the right, I get 0, negative 2.5, negative 2, negative 6.5, which is exactly the matrix that we found. It's exactly right. Nice, right? So the way that we did this, the more systematic way of finding the coordinate vectors relative to the new, and then making that making those the columns. I could have found this much simply by just putting down the basis vectors that are new and then the old ones. Make your calculator do the work, and then immediately I get this, the transition matrix from the old to the new. Any questions about transition matrices and how to find them using this method? Is this clear? Is this good? Okay. So now that we have that, wouldn't we also be interested in finding the transition matrix from the new to the old? So what if I want to find the transition matrix of P from B prime to B? What do you think this would entail? So we know that what? We know that the coordinates of V with respect to the new is equal to the matrix, the transition matrix from the old to the new, multiplied by the coordinate vector relative to the old, right? But now I want to go the opposite way. Flip old and new. Yeah, you can flip old and new, right? We just rearrange these things and then we perform row reduced echelon form. But what is really the underlying matrix? How is that matrix that we're looking for, the transition matrix, how is that related to the original transition matrix that we found? So I want to do this. I want to go from here, and I want to go from saying V to the old equals question mark from the new. Do you see here? This here goes here. This here goes here. I want to know, what is this going to be? How is this matrix? How is the transition matrix from the new to the old related to the transition matrix from the old to the new? What is the relationship between these two? What does it have to be? What do they have to be? If you think about it, how would I get rid of? Right, the inverse, right. How to get rid of this matrix and just have this alone? I would have to multiply this by its multiplicative inverse. You see that? It would have to be the inverse of this. So these matrices are inverses of one another. So this matrix here from B to the B prime to B, these are inverses. And doesn't that make sense? If I say, hey, I want to go from the old to the new and then new to the old. I want to go from the old to the new and then come right back. I would have to do the inverse and vice versa. So the transition matrix from the old to the new, from the new to the old, is equal to the transition matrix from the old to the new, but inverse of one another. And same thing goes for the transition matrix from the old to the new. It's the same thing as saying the transition matrix from the new to the old. They're inverses of one another. Or in other words, the matrix, transition matrix, when you multiply them together, equals the identity. And similarly, the other way around, right? So these matrices are invertible, obviously. They have to be invertible. Does that make sense, guys? It's a bit different now. We're dealing with a different level of computations. Now these computations are not just merely, oh, I'm multiplying. These start to see that, like, now instead of just saying, hey, what is this multiplied to? Oh, this equals this, and you move on. Now you're dealing with, I don't know if you start to see that yet. Now you're dealing with significance as to why we multiply these numbers and what is the significance of these vectors themselves. Now they're not just merely vectors for the sake of being vectors. Now these vectors have a more, and particularly these vectors have a geometric significance with respect to the bases. So now we're elevating our understanding of matrix multiplication. So at first it was just a technique, a procedure, and now we have much more meaning to it. Now we're dealing with transition matrices from one basis to another. And that's a different level of significance. Okay, so let's do a problem like this with 3 by 3. So let's say I have an old basis. Call it B, U1, U2, U3. And U1 is 2, 1, 1. U2 is 2, negative 1, 1. And U3 is 1, 2, 1. The new basis is W1, W2, W3. My new basis have the vectors 3, 1, negative 5, a 1, 1, negative 3, and negative 1, 0, 2. We got a new basis and an old basis. And I have a vector v. So my vector v that they give me is negative 5, 8, negative 5. And the first thing they asked me to do is to find v in terms of the old. And once I find v in terms of the old, I want to find v in terms of the new. But I want to find v in terms of the new basis using a transition matrix. Which takes things from the old and transitions them to the new. So for this one, there is no way to go get around it. For this starting position, there's no way to get around what I have to do. To do this, I need to do V equals, and then do C1 U1 plus C2 U2 plus C3 U3. There's no way around doing this first step. This is just straightforward standard. Find the coordinate vector relative to the basis B. So long story cut short, U1 would be what? This equation would be 2, 1, 1. This is 2, negative 1, 1. And this is 1, 2, 1. Multiplied by C1, C2, C3. And V was what? V was negative 5, 8, negative 5. And I want to find what C1, C2, C3 is. And I would recommend using the calculator for this again. So I'm going to use a 3 by 3. So I got 2, 2, 1. 1, negative 1, 2, 1, 1, 1. And then my column vector is negative 5. Whoops. I did not mean to press that. Negative 5, 8, and then negative 5. And then I'm going to add A and then do the inverse, then multiply that by B. And I get 9, 9, 9, negative 5. I get 9, negative 9, 5. So this is the coordinate vector of the matrix of the vector that they give me with respect to the old. So it's 9, negative 9, 5. Okay. And now I want to compute the transition matrix. So how do I get the transition matrix? Well, now I have to create a 3 by 6 matrix where the first 3 columns are the columns of the new matrix, of the new basis. The new basis is what? 3, negative 1, 5. So let me switch back. So we found the coordinate vector relative of V with relative to the old basis, 9, negative 9, 5. Now I want to find the transition matrix from the old to the new basis, which implicates that I need to use the column vectors being the new column vectors, the new basis. So it becomes 1, 1, negative 3. This is negative 1, 0, 2. And then the old are what? Are 2, 1, 2, 1, 1, 2, negative 1, 1, 1, 2, 1. I want to find the row reduced echelon form. And the expectation is that this is 1, 0, 0, 0, 1, 0, 0, 0, 1. And on the right, that's going to be my transition matrix P, B to B prime. So I'm going to go back using the calculator this time and then go to the matrix. And now I'm going to have a 3 by 3, a 3 by 6 instead. And so then my new matrix now is 3, 1, negative 1, 2, 2, whoops, 2, 2, 1. I got negative 1, 1, 0, 1, negative 1, 2. Then I got 5, -3, 2, 1, 1, 1. And then I'm going to find the row reduced echelon form of this matrix. And when I get it, I get exactly what I expected, the identity being on the left, the 3 by 3 submatrix on the left, and then I get 0 0.6, 1.6, 1.4, 0 0.4, negative 0 0.6, negative 1.4, 0 0.5, 2.5, and 3. And so I found the transition matrix that goes from the old to the new. So that's going to be the transition matrix P. B goes from B to B prime of 0 0.6, 1.6, 1.4, 0 0.4, negative 0 0.6, negative 1.4, 0 0.5, 2.5, and 3. Does everybody see that? Was everybody able to get that using their own calculators? So any questions about this step here? The transition matrix using the row reduced echelon form of that matrix. And on the right side, that's going to be your transition matrix from the old basis to the new basis. So when you multiply every coordinate vector relative to the old basis, when you multiply those coordinate vectors relative to the old basis by this transition matrix, you immediately automatically get the coordinate vector of that vector in terms of the new basis. So we're not done with this yet. I still want to find what? I want to find the coordinate vectors of the new relative to the new basis. So I have to multiply this by the transition matrix and then multiply that by the coordinate vector of the old. So the coordinate vector relative to the new basis will be 0 0.6, 0 0.4, 0 0.5, 1.6, negative 0 0.6, 2.5, 1.4, negative 1.43. Multiply this by the coordinate vector that we found originally, 9, negative 9, 5. So when I multiply this, I should get, and again, this is the transition matrix from the old basis to the new basis. And this is the coordinate vector relative of V relative to the old basis. And I get my new basis. So let me do that here. So again, this might be the last time we use this calculator here. So let me just edit this one first. So this is 9, negative 9, and then 5. Okay. And then 3 by, should be 3 by 3. I get dot, yeah, 0.6, 0.4, whoops, 4.5, 6, negative 0.6. Oh. This is 2.5. 4, negative 1.4, and 3. Okay, so then now when I multiply this, A matrix times the B matrix, I get a strange number, a strange column vector, but it is what it is. 4.3, 32.3, and 40.2. This is going to be the coordinates of the new of the vector with respect to the new basis. So any questions, guys, about this? Now, how just to make sure, how are we sure that these are indeed the coordinate vectors relative to the new? You'll just solve the equation. You would set up the same equation here, but instead of using U1, U2, U3, you're going to use W1, W2, W3, and do the same exact thing here. So just to verify that, let's do that. So our coordinate vectors here are going to be, I'm going to use a new matrix here. C, 3 by 3. And these vectors are going to be 3, 1, negative 1, 1, 1, 0, negative 5, negative 3, 2. And then D is going to be 3 by 1. It's going to be the vector negative 5, 8, negative 5. And so when I take the matrix that I plugged in here, take the inverse of it, and multiply that by the column vector that I have here, I should get the same thing. So I didn't get the same thing. So something is not right. Did I type in everything correct? It looks like I have. Let me just see. What is A again? Just want to make sure that everything is okay. So A is that. And then B is 9, negative 9, 5. And that's what I get, right? When I multiply A by B, I got 4.3. Okay. And then C, what is C? C is 3, 1, negative 5, 1, 1, negative 3, negative 1, 0, 2. Yep. And then D is negative 5, 8, negative 5. Oh boy, oh boy. So there's like a little discrepancy here. There should be the same numbers. Should be the same. Do you guys get the same thing or do you guys get something different? 3, 1. Sometimes it's just about one number being wrong. 3, 1. Negative 1, 2, 2, 1, negative 1, 1, 0, 1, negative 1, 2, 5, -3, 2. So I remember doing this, and what did I get? Yeah, everything looks right. Let me just make sure. Make sure that I'm doing this right. Yeah, all the numbers match up. So there might be something that we did incorrect in the beginning. -9. Yeah. So I'm gonna look into that. I don't know exactly why the discrepancy is there. There shouldn't be a discrepancy. So when I multiply this out, I get this. But when I do this, I get something different, which shouldn't be the case. I get this instead. Yeah, I'm gonna have to look into that and to see. Might be something, a tiny little. I feel like it's just a tiny little error that I can't quite pick out at the moment. So yeah, it's always good to check. Always good to verify. But yeah, I'll look this over and I'll get back to you guys next Monday.